Inverse variation involves two quantities that change in opposite directions. So if x gets bigger, y gets smaller. An example of an inverse variation graph would be one that looks like this. As the x's get bigger along the x-axis, you can see that the y's get smaller. They get closer and closer to the x-axis. The general equation for inverse variation is y equals k divided by x. This k stands for the constant of variation. It's always the same in a particular inverse variation problem. We can find the constant of variation by multiplying. If we look at this equation, y equals k over x, we multiply both sides by x, we see that k equals x times y. We can use this principle to help us find the constant so that we can write specific equations for inverse variation problems. Now, one thing to note is that the constant is never going to equal 0. If the constant never equals 0, that tells us about x and y, that they're never going to equal 0 either. So the point 0, 0 is not on the graph of an inverse variation problem. So let's look at a few examples and let's see how these variables vary inversely to each other. We can find an inverse variation equation from a graph. So here we have the graph, and we can tell that it's inverse because as the x's get bigger, the y's get smaller. It also does not contain the point 0, 0, so we're good. Now, let's choose a point on this graph to help us find our constant of variation. Looks like 2, 120 is a point on the graph. That means that when x is 2, y is 120. So we know that y varies inversely as x. We have y equals k over x. And if we plug in our two values, we can see that 120 equals k divided by 2. We multiply these, we can get the constant of variation for this problem. 2 times 120 is 240. So 240 equals our constant, and the specific equation for this particular graph is y equals 240 divided by x. Once you have this specific equation, you can find other pieces of information about the inverse variation problem. So let's just check this equation that we wrote. We know that 640 is also on the graph. So to test that, we would want to see if 40 equals 240 divided by 6. That's true, so our equation is correct. We can also look at tables to find inverse variation equations. Remember, we're looking for as one variable gets bigger, the other gets smaller. So if we look at the first table, as the x's get bigger, the y's get smaller. You can see we went from 48 to 2. That's getting a lot smaller. Our equation for inverse variation is y equals k over x, which means we can find the constant by multiplying multiplying x and y. We know our table represents inverse variation if it always multiplies to be the same thing. So looking at that first table again, we have 1 times 48, 4 times 12, 6 times 8, and 24 times 2. They always multiply to be 48. So this tells us our constant. And the equation for this table would be y equals 48 divided by x. So we could use it to make our table longer and find other points that we can't necessarily see on the table. Let's look at the second table. As the x's get bigger, the y's also get smaller. So this could be inverse variation. Now we want to check to see if they multiply to be the same thing every time. 2 times 3, 4 times 1 1/2, 6 times 1, 12 times 1/2. What do they all multiply to be? 6. So in this case, our equation for this table is y equals 6 divided by x. We have one more table listed, and this is an inverse variation table. However, we don't have all the values filled in. So we need to use our context clues. We see one x and y that go together. And to find the constant, we could do x times y. 2 times 120 is 240. So this gives us our equation for this table. Y equals 240 divided by x. We have a lot of x values here, so we can use our equation to fill in the rest of the table. For the first one, we would find y equals 240 divided by 4, so that would get us 60. Then for the next one, we would have 240 divided by 6, which would get us 40, and 240 divided by 8, which is 30. So once we have that equation, we can find all sorts of information. That's why the equation is key in these inverse variation problems. Frequency varies inversely with the string length. Just like with direct variation, this is an important thing to look at. Y varies inversely as x. So frequency is the y, and string length is the x. Our generic equation is y equals k over x. So if we want to find the equation for this particular frequency of this string, we would need to look at these pairs that are given to us in the table. 20 and 120, 40 and 60, 60 and 40, and 120 and 20. When we multiply all of those, we get a constant of 2,400. So the specific equation for this situation is y equals 2,400 over x. Or if we want to use the variables we were given, we would say that frequency equals 240 divided by the string length. We want to find the string length when the frequency is 30 hertz. So if we plug it into our equation, we get 30 equals 2,400 divided by the length. Now let's solve for the length. To do this, the first thing we have to do is multiply both sides by the length. So 30 times the length equals 2,400. Divide both sides by 30. And we get a string length of 80, and in this case it's centimeters. So here was a perfect example of where getting that equation first helps us find more information about the situation. In kickboxing, the force needed to break a board varies inversely with the length of the board. So force varies inversely with the length. So this is y varies inversely with x. So the length is the x. Let's get our equation set up. Y varies inversely as x. So in this case, force varies inversely as the length of the board. If it takes 5 pounds of pressure to break a board that is 2 feet long, we want to find out how long it would take, or how long a board would be that takes 8 pounds of pressure to break. So let's take the two pieces of information that go together and find our specific equation for this situation. When the force is 5 pounds, the length is 2. So when we multiply this, we get k equals 10. So our specific equation is force equals 10 divided by the length. And we want to find how long a board would be that takes 8 pounds of pressure to break. So we know the force. We could plug this into our equation to say that 8 equals 10 divided by the length. And now it's just a matter of solving this equation. Multiply both sides by L, so you get 8L equals 10. And then you could just divide both sides by 8, and that'll give us the length of the board. So in this case, the length of the board is 5/4 or 1.25 feet. The number of days it takes a movie crew to set up for a stage scene varies inversely as the number of workers. So the number of days varies inversely as the number of workers. This tells us our y and our x. Let's think about this for a minute. The number of days varies inversely as the number of workers. More workers, fewer days. Less workers, it's going to take you longer. So our generic equation is y equals k over x. If we want to use the specific values that were given to us, we would say days, d, equals k over the number of workers, w. So a stage can be set up in 3 days by 20 workers. These are numbers that go together, and we can plug them into our equation to find k. So 3 days equals k divided by 20 workers. So k equals 60. This lets us know what our specific equation is. The days equals 60 divided by the workers. Now that we have this specific equation, we can use it to answer the question. The question is, how many days would it take for only 12 workers to do it? So let's plug that in. We want to find days, so that stays d, equals 60 divided by 12 because we have 12 workers. So 60 divided by 12 is all that we have to do in this case, so it would be 5. It would take 5 days to set up this particular movie set. And we don't always have to vary inversely just with x and y. We can also have squareds and square roots, so we're going to look at a couple of those examples too. So a varies inversely as the square root of b. So when we think about our equation, it's usually y varies inversely as x. In this case, we're going to change it a little bit to reflect that it varies inversely as the square root of b. So a varies inversely as the square root of b. Now it says that a equals 4 when b equals 64. This lets us know what values go together in order to find our constant. So 4 equals the constant divided by the square root of 64, which means that 4 equals k divided by 8. And when we multiply, we can get our constant. K equals 32. Now that we know this information, we can write our specific equation. Our specific equation is going to be a equals 32 divided by the square root of b. Now we can answer any question about this particular situation, but we want to know what happens when b is 4. So a equals 32 divided by the square root of 4, which means a equals 32 divided by 2. So a equals 16. So the only thing that was different is that instead of writing over x, or in this case over b, we wrote over the square root of b because it varied inversely as the square root of b. Alright, last example. A body's weight varies inversely with the square of its distance from the center of the earth. So weight varies inversely as the square of the distance. This will be a common occurrence in a lot of the things you look at for physics. This has to do with planetary motion as well. You can look up Kepler's law and you're going to see an over d squared in that. For this particular problem though, we have a chicken, and this chicken weighs 12 pounds when it is 5,000 miles from the center of the earth. So using this situation, we can plug those two values in, the weight is the constant divided by 5,000 squared. Now we can find our constant. It's going to be big, but that's okay. Get out your calculator. 12 equals k divided by 5,000 squared, which is 25 million. And when we multiply these two things out, you're going to get k equals 25 million times 12, which is 300 million. Careful not to lose any of those zeros or you're going to get a totally wrong answer. Now that we have our 300 million, we can write our equation. Weight equals 300 million. I think I need one more. Yep. Divided by the distance squared. So now that we have this equation, we can finish answering the question. How far is this little chicken going to, or how much is this chicken going to weigh when it is 10,000 miles from the Earth's center? So this chicken will weigh 300 million divided by 10,000 squared. So this chicken is going to weigh 300 million divided by 10,000 squared is 100 million. So 300 million divided by 100 million, this chicken will weigh 3 pounds when it is 10,000 miles from the center of the earth. Although what the chicken is doing out there, I have no clue. Inverse variation involves two variables that change in opposite directions. As one thing gets bigger, the other thing gets smaller. So in this case, the generic equation is y equals k over x. This is what makes it different from direct variation. Also, we're never going to have the point 0, 0 on our inverse variation graphs because k is never going to equal 0.